lots of different things, right? So that's where this comes from, okay? Now, the next thing we'd maybe like to do is understand what the solutions to Laplace's equation behave like. And just like in the case of the heat equation, we derive the fundamental solution. We're going to do that again here in the case of Laplace's equation, okay? And so in order to get there, we'll start with a homogeneous problem, okay, on an unbounded domain, right? So when I wrote down this, right, we started on a bounded domain. But remember, just like with the heat equation, certain things are easier on unbounded domains because I don't have to worry about interactions with the boundaries, okay? So I'm going to make a couple claims and then we'll prove them, okay? So first claim is if the Laplacian of u equals 0 on Rn, and otherwise u is harmonic on Rn, okay, then the following things are true, okay? W of x is equal to u of x minus y. It's also harmonic for any y in Rn. This should be reminiscent of the kinds of games we played with the heat equation. And this is due to translation symmetry. Second of all, this one takes a bit more work. Any rotation of the solution u is also a solution. So it's also harmonic, okay, for any rotation matrix, okay? And we can define these as R is going to rotate our coordinates such that R transpose R is equal to I, and the determinant of R is equal to plus or minus 1, right? So we're not doing any changing of the size of vectors. We're just rotating their coordinates. So rotation symmetry. Okay, we'll prove these, and then I think we'll be done for the day. So, so these are the ingredients that we're going to need to put into our analysis in order to build the fundamental solution. Let's prove both of them. So to start with, we'll let W of x equal u of x minus y. Y is in Rn, okay? Well, then the partial with respect to xi of wx is equal to the partial with respect to xi of u of x minus y. This is equal to the derivative with respect to z, what I'll call u of z, where z is equal to x minus y, just the shifted coordinates, right? Because if I differentiate, y is just a constant, it drops off, okay? So this implies that the xy's Laplacian of wx, it should just be equal to the zy's Laplacian of uz, which we know already is equal to 0, right? Essentially because dxixi of wx is equal to zi by linearity of uz. Okay. So w is harmonic, okay? First property that we wanted to prove. Now on to the second one, okay? Now if we let w of x equal u of y, or y is equal to, sorry for the sounds of the suburbs there, is equal to r of x. R is in SON. R equals Rij, right? Some rotation matrix. I'm just giving us a little bit of notation to work with. dxj of wx can now be computed by the chain rule. Okay, what's that look like? Well, remember now, y is going to be this, right? So I got to deal with all the coefficients that are going to pop up from the rotation matrix. I equals 1 up to n. So I get dyi u of y, dyi dxj. This is equal to what? Well, I just look and see what my rotation matrix is. It's just going to be dyi u of y rij, okay? Well, using this fact, right, I can take the x Laplacian of w of x, right? This is equal to the sum j equals 1 up to n of dxj xj of w of x. This is equal to the sum from j equals 1 up to n of dxj. Now the thing that I already have, right, which is I equals 1 up to n dyj uy rij. Cool. Now, if I go a step further, right, I can replace the dxj now using this knowledge, right? Because dxj essentially is the operation of taking the sum over rij, the sum over dyi, right? So I can say, well, now this whole thing is going to be equal to j equals 1 up to n, right? Take this, replace it what I've learned that it's equal to up here, okay? It's going to get a little bit hairy for a bit. So the sum from k equals 1 up to n of dyk or kj, got a few different subscripts floating around here. I equals 1 up to n dyi uy rij, okay? And this is equal to the sum from I equal 1 up to n, k equal 1 up to n, dyi yk uy, and then I got these y equal, or j equal 1 up to n rij rkj terms here, okay? But remember now, okay, R transpose R is equal to I, and this actually implies that, I'll write it like this. This implies that the sum from j equals 1 up to n of rij rkj is equal to 1 if I is equal to k, and 0 if I is not equal to k, sort of like a Kronecker delta. Okay, so this thing, right, when I equals k, it's going to be 1, it's going to be 0 otherwise. Okay, cool. Well, then that actually collapses this double sum down to a single sum, and we get the x Laplacian of w of x now is equal to the sum from I equals 1 up to n of dyi yi uy which is just the y Laplacian of u of y, which is equal to 0, which is what we wanted to prove. Okay? So we've proved translation symmetry and rotational symmetry. And so rotational symmetry is a fundamental property of solutions to Laplacian of u equals 0 on Rn. So any solution is you can rotate it and it should look the same. Okay. We're going to do like what we did in the case of the heat equation, and we're going to seek a fundamental solution. Okay. That has this rotational symmetry. Phi of x is equal to phi of Rx. Okay. Analogous to the heat equation case. That's what we'll do in the next lecture with this symmetry, okay? And so the question then is, what form must this solution take, okay? Stop and think about that for yourself. Anything that's rotation symmetric, right? What does it need to look like? It should only depend on the radial variable, right? So u of x should just be equal to some function v of the magnitude of x, or just v of r, just a radial solution. So that allows us to collapse the Laplace equation in n dimensions down to just a one-dimensional equation.